Welcome to Train Signal. I'm Chris Bryant, CCIE number 12933, and this is video 11, Subnetting, VLSM and CIDR. And those of you who have seen any of my articles out on the web or used my materials in the past to earn your CCNA, you know that I'm very big on my students learning how to subnet correctly instead of relying on charts. And there's a reason for that. I'm stunned to this day at the number of vendors out there, and this includes Cisco in some of their books, where they'll teach you the interesting number trick or the magic octet trick, or some of the other vendors on the web will give you a 3-page long chart and say, here, memorize this for the exam. Well, I will tell you firsthand, real world and exam room, that stuff does you no good whatsoever. Because even if you managed to get the CCNA years ago with those charts, and it was possible years ago, not anymore, then you're going to get nailed the first time you actually try to use it. Because you're going to be either in a job interview or you're going to be out in the real world, and you're going to need to draw some basic knowledge of subnetting, and you wouldn't be able to do it if you relied on memorization. Because how long do we remember things that we just memorize for an exam? I don't care if it's junior high school or the CCNA or CCNP or anything. You just don't retain it very long. And the only way to get really good at this is to practice it. So we're going to do a little bit of a review here. We're going to look at the major network classes. We're going to look at how to determine the number of valid hosts and subnets. That should be familiar to you from CCNA, because we've got to know that, because now we're going to the next level. We're going to the next level of subnetting. We're going to do some VLSM. We are going to create a VLSM scheme right here live. I'm going to have the networks up here. I'm going to have the number of hosts we need, and we're going to walk through how to do it. But I want to impress on you now, and I will mention it again at the time. You can watch me do it all you want to, and you can learn from that. But the only way to master it, and the only way to be prepared for it in the exam room, is to practice it on your own. It's to practice it on your own. And you don't need to go out and buy a lot of expensive practice exams to do that, because I'm going to show you just how to write your own questions. I'm going to show you how to write your own practice. And if you just do that for 10 or 15 minutes every day leading into your exam, you will be amazed at how well you do on exam day and in the real world. It's really amazing. You'll see how simple VLSM really can be with the right approach. Then we're going to go into a short discussion about how RIP and IGRP handle incoming routing updates. I like to call this part more than you ever wanted to know about RIP version 1 and IGRP. And you may have thought you left those behind, but not quite. Cisco would like you to know a little more about that for your CCNP. We're going to revisit route summarization. And again, that's something I'm very big on in my CCNA course. I'm very big on it here. We'll do that, or depending on what order you're watching the videos, have done that with each protocol. But we're just going to go over the basics again of it in case you're, just feeling a little uneasy about it. You'll see again that it's very simple. And I'm going to show you one classic gotcha that I see a little more in the real world than in the exam room, but it can have bad consequences either way. And then finally, a very short discussion of CIDR. And if you've read anything about CIDR and you wonder how you're going to keep this short, you're going to see. So let's get started here with a quick question. Now, what is subnetting to begin with? What are we doing? We're taking a major network number and we're dividing that number into smaller, more manageable parts or networks or subnets. And this is done by borrowing host bits. And those of you who got your CCNA recently, you know the rule. You never, ever, ever borrow network bits for subnetting. Can't do it that way. Subnetting is really just like taking a pie and cutting it into slices. That's all you're doing. You're cutting it into slices. Now, for your CCNA, the slices were the same size, right? You were asked, basic subnetting questions. We got 6 networks and they're all the same size. What subnet mask do you need? Well, in the real world, how often do we really get a network where all the segments are going to be the same size? Doesn't happen very often. So for the CCNP, the stakes are going to be raised. Your network slices, so to speak, your subnets are not going to be the same size. And we're going to walk through totally from the beginning a VLSM scheme so you can see how to do it. But just first, a quick review of some old friends here. Our classful networks. You know the first octet of each one of these. You may not be familiar with that number behind the slash, though. And if it's been a while since you looked at your CCNA, you might not know what that is. That's called prefix notation, and it's pronounced /8, /16, /24, however you see it there. And what the number refers to is the consecutive number of ones at the beginning of the network mask. It's easier to type, and it's easier to say in a meeting instead of saying, oh, we're going to do subnet mask of 255, 255, 255, 240. Instead, you could just say /28. So, again, we have no masks for Class D and E. Class D, as I'm sure you recognize from that first octet of 224, is reserved for multicasting addresses. And 240 and up, depending on which definition you read out there, it's either reserved for future use or experimental. All I know is we can't use it on a Cisco router. That's the important thing. We cannot take addresses from networks D and E and apply them to host devices or routers. Now, I put 127 up there because that's the one missing number, and I know that you know that that is the loopback address range. But just a detail that I see people get mixed up on a little bit. You cannot put an address from that range onto a Cisco loopback interface. That's not the kind of loopback we're talking about. And here on this router, let me call that back up and do an escape. If I try to configure a loopback, and we'll just call this loopback 200, and give it an address, say, of 127.115, of course I wouldn't get away with that, the mask anyway, I can't give it an address from that range. I'm immediately given the message, not a valid host address. And that's another great thing about Cisco routers. As you develop VLSM schemes and as you put them into production, if you're trying to give a router an IP address that you shouldn't be giving it due to your VLSM scheme, the router's going to tell you, hey, you know, that's not a valid host address for what you've set up. Here it's telling us that because this is a reserved range. I'm pretty sure I would get the same thing if I tried to give it an address of 224.0.0.200. Something like that. Let's try that mask again. Not a valid host address because it's a reserved D class address. So, just keep those in mind because we have to know these. You have to be able to look at a network address that begins with 150 and say, okay, I know that's a Class B, and it's got a network mask of Class 16. It's not just, you know, stupid memorization tricks. It's not just like they're going to ask you a question like that. You have to know that to be able to do what we're going to do as we proceed with this lesson. First off, let's revisit one of the two questions that we learned how to answer in your CCNA studies. And if you didn't have this when you got your CCNA, it's a good time to catch up. How to determine the number of valid hosts per subnet. And here we're asked how many valid hosts exist on the subnet 172.12.12.0/24. The formula for solving this is that the answer is 2 to the nth power minus 2, where n equals the number of host bits. Now, what are the host bits, you may ask? Well, what we've done here to identify the host and subnet bits is written out the network mask for this subnet and then the subnet mask right under it. And what we've got, first off, we've got to be able to look at that address and say, I know that's a Class B address. I know that has a /16 network mask. I know what that looks like in binary. So really, Cisco's already asked you 3 questions right off the bat in one question. You know, do you know what class this is? Do you know what the network mask is? Do you know what that /24 means? And the subnet mask goes right under it. Now, the host bits are found where the network mask has a 0 and the subnet mask has a 0. So the number of valid hosts on this particular subnet would be 254. It's 2 to the 8th power minus 2. Now, depending on when you got your CCNA, the formula for the following question has changed. And this is determining the number of valid subnets. we would look at the same kind of question, but we have to identify the subnet bits. And again, the subnet bits are where the network mask has zeros and the subnet mask has ones. So again, this one's very clear cut. There are 8 subnet bits. And that's what we're using in this formula, but notice it's 2 to the nth power, where n equals the number of subnet bits. There's no -2 anymore. And it was that way for years. And Cisco has finally come around in their exams to accept that subnet 0 and the all ones subnet are valid. If you're a little fuzzy on what those are, you're going to see what they are when we develop a VLSM scheme. And using the previous example, with this formula, we would have 256 valid subnets with 254 valid hosts per subnet. Now the key here is, the real-world theory, is that Cisco routers have had the use of subnet 0 enabled by default for years. Well, let's do a quick show config here on router 1. And you can see right up here, IP subnet 0. I didn't configure that. That's configured by default. I don't remember the last time I took a Cisco router right out of the box and it did not have IP subnet 0 on it. But Cisco was still holding it because in network theory, you're not able to use those. And it got confusing because then people would go on the workplace and say, well, we're using subnet 0. So Cisco's finally come around in their written exams and changed this formula, thank goodness. But you could see that the default setting was indeed IP subnet 0. So we have to be just clear as crystal about how to figure these two things out. How many valid subnets do we have with this network number and how many valid hosts? Because we're going to put all that into action when we're developing a VLSM scheme. And that's what we're going to do right now. I shouldn't even have to put that /16 up there, of course, because you know by looking at that that is a Class B network and it has a network mask of /16. So that's two things we've been asked right off the bat. And Cisco may ask you to create a short VLSM scheme on the exam, but this is also very handy in the real world. I've had students not only pass the exams with my BSCI materials, but they have put working VLSM schemes out there on networks by doing what I'm about to show you. And this works, and there are no tricks. It just works. We've got 5 networks, and this time, like I said, we're raising the stakes. We've got a different number of hosts needed on every single network. So we have to know, just by looking at this, when you're a CCNP, I should be able to hand you this, and 30 minutes later, or less, much less probably, you've got the scheme ready to go. Here are some pointers, though, while you're doing that. Always keep future growth in mind. Now, on an exam, if you ever have a scenario where future growth has to be taken into account, Cisco's going to tell you that. They're not looking to trick you. They're going to say something like, hey, you got 20 hosts that need to be on the subnet right now, but over the next 4 years, you're going to add 20 per year. Well, of course, right now, when we're developing a scheme, we don't have any idea about that. So we want to leave ourselves some breathing room. When we go through this scheme, I'll show you one of the networks that we're going to create, where on the exam I would say, okay, here's what I would do, but in the real world I would do something a little different. And plan twice, configure once. You may want to plan thrice. And by plan, I really mean just by checking your math. Check your math. You don't want to troubleshoot a VLSM scheme after you put it out there on a production network. If it happens, then I know that you will know how to fix it. But if you just take 20 or 30 extra minutes to walk through your scheme one more time before you put it out on a network, that 20 minutes of extra planning can save you hours of trying to figure out what's going on your network. Now again, you may not have to come up with any full-blown VLSM scheme during the BSCI exam like we're going to do here, but as a CCNP, you should be able to. And here's a method that has worked for me, it's worked for my students, it's worked in production networks all over the world, where you look at the major network number you're given, and when I'm doing VLSM schemes, I like to start with the biggest networks first. Some people like to go the other order once you've practiced this enough. In the real world, if you want to do your small subnets first, go right ahead. But in this case, and in every network VLSM scheme I develop, I'm always asking this question. What is the smallest subnet that can be created with all the host bits set to 0? And that will become clear to you what that means as we walk through a few of these. Let's look at network A. We need 200 valid host addresses. So immediately we need to know, okay, how many host bits is that going to take? And it's going to take 8. 7 host bits would not be enough. 2 to the 7th power minus 2 is not bigger than 200. It's 126. But 2 to the 8th power minus 2 is 254. That gives us 254 host addresses. So here I've drawn out the network number in binary, 150.50.00. This is subnet 0. This is what we used to not be able to use on an exam, but now we can. And we're going to put a 24-bit mask right next to it. And that leaves us 8 host bits. Now you remember, in this formula, we are subtracting 2. Remember when we're creating the number of host bits or figuring out how many valid host addresses we've got on a subnet, we still subtract 2. That has not changed. And the reason we're doing that is because we are subtracting the first number in the range and the last number, because those are truly invalid host addresses. The first one is the network number itself. The value of that string on the top, 150.50.00 with all the host bits set to 0, is the network number, and it is 150.50.00. We cannot assign that to an interface. We can't put that on a host device. But there's one other one, and it's the broadcast address. And every subnet has a broadcast address. That's what you really have to get used to now with developing VLSM schemes and becoming a CCNP. You know, when you're getting an NA, it's like, oh yeah, 255, 255, 255, 255. That's the broadcast address. But it's not the only one in your network. Every subnet has its own broadcast address. And it is the value of the string with all the host bits set to 1. So what would that be here? If all those hosts in the end of 150.50.00, and actually they're in blue for this one, if those are all set to 1, what's the value of this entire thing? 150.50.0.255. That's the other invalid address. This is the chart we're going to use as we go along, and we'll be filling it in. I didn't want to fill it all in advance. But you can see that network A has the subnet and mask is 150.50.00/24. You see the network number that we came up with. You see the broadcast address at the end of the column that we came up with. And everything in the middle is fair game. Everything in the middle is a valid IP address that can be assigned to a host device or a router interface. So that gives us 150.50.0.1 through 254. So that's how we get started. And you want to keep this chart as you go along, and we're going to keep coming back and revisiting it. Because now we've got to come up with the plan for network B. And how we start that is with the next number up from the broadcast address of the last subnet that we created. So that was 150.50.0.255. The next number up from that in binary is 150.50.10. Because 255, of course, as you know, that octet is full. So the next number up would set that to 0, but the next octet would go up to 1. If we add 1 to that octet, that's what we end up getting. So that's actually our next network number, 150.50.10. But now we need to come up with a subnet mask for it. And network B required 50 valid host addresses. Now using the valid host formula again, and you see that we're continually revisiting that, we would determine that 6 host bits are necessary. 2 to the 6th power minus 2 gives us more than enough addresses. So what's the smallest subnet then that can be created with all the host bits set to 0? Well, it would be 150.50.10/26, because that combination leaves us 6 host bits there at the end where both of them have a 0, both the network number and the mask. Now, you need to be careful here when you start converting these out. If all of the host bits are set to 0, that value is pretty easy because that's already done. We can see that. But be careful here at the end. What if all the host bits are set to 1? You've got 6 host bits at the end of that address, and if they're all set to 1, the value is 63. Because remember, we're going 128, 64, 32, 16, 8421. If all the host bits are set to 1, we get 1.63, 63 for the final octet. And that is our broadcast address. Those two addresses right there are the two that we cannot assign. Everything in the middle from .1 to .62 are valid addresses. So let's go back to our chart and fill that in. Let me change the font size here a bit. So now we've got network B, and we determine that the subnet and the mask for that 10/26. And now you see the real VLSM come in because our networks are not going to be using the same length subnet mask. That's why we call it variable length subnet masking. You call it that in the CCNA too, but you're not really doing it yet. 150.50.10 for our network number. Let's go down to the broadcast address. If you want to put the broadcast address next in your column, that's fine. 1.63, so we know that everything in the middle of that is a valid host address. This may push it over, let's see. Yeah, it did. 51, 1.1 through 62. Those are our valid host addresses. So now we're creating a VLSM scheme. We're getting it done. We've already come up with 2 subnets and 2 masks, and we're going to do the same thing for the next couple of networks that we were given. Now, I'm not much on going into the exam room and writing a bunch of stuff down because I think you should know it and not have to write a lot of stuff down. You don't want to write notes as soon as you walk into the exam room, especially at the CCNP level. The one thing you might want to write out, though, in advance, I would write a chart like this and just put the 5 headings. You know, network mask, subnet and mask, network number, valid host, and broadcast address, because that can help you structure your answering a bit. But that's up to the individual. That's up to you. Now, we're going to create our next subnet. And the next subnet is one value up from that broadcast address that we just came up with. The broadcast address was 150.50.163, so the next value up is .64, and that's going to be our network number. 150.50.164. But now we've got to come up with the number of host bits. And we needed 25 valid addresses. Now, 5 host bits would get the job done. That's going to yield 30 valid host addresses. 2 to the 5th power is 32. Take the 2 off, you got 30 left. In the real world, that's getting a little close. So you might want to rethink that. But in the exam room, I would just make them as tight as you can, unless they tell you to, worry about future growth. So again, we simply write out the mask. That's going to give us the smallest subnet possible, and the result is 150.51.64/27 for the network number. But what is the value if the last 5 bits are set to 1? Be careful with this. Before I put the answer up, I want you to tell me, or tell yourself, if the last 5 bits of that network number are set to 1, what is the value? I need to change the font, and while you're figuring that out, you may already have. You'll see that it is 95. That's our broadcast address for this subnet. Now, if you got that, congratulations, because that tends to trick people because they're used to everything else in the address being a 0 or everything else in the octet. But that's not true. The 64-bit is already set. Please note that when you're coming up with the broadcast address. If the network number is .64, there's no way the broadcast address can just be, 31. which is what you'd get if you ignored that 1. Because the last octet for that broadcast address, what does it look like? That's already set the first 3 bits. Then we're setting the last 5 to 1. So that's 95. If you ever do this in the exam room or the real world, and your network number octet is higher than your broadcast address, you need to go back and check your math real quick. I guarantee you probably just did something like we were just talking about right there. No big deal. We want to note that here and not note it on exam day. So let's go back to our chart, and we're going to put in network C. The subnet mask itself, it's going to be 150.51.64/27. This is pretty cool once you get it rolling, isn't it? Because now you're actually doing the stuff. That's what it's all about. 65 through 94, because your broadcast address is 150.51.95. So now you've done network C. Now we'll take care of the other 2 networks, really the same fashion. And for network D, the next subnet is going to be 1 value up from the broadcast address we used for C, and that makes it 150.51.96. Network D needs 5 host addresses, so technically 3 host bits are required. I say technically because that's what I would do on the exam if they didn't mention anything about future network growth, because 3 host bits will give us 6 valid host addresses. In the real world, I'd be really careful about that, because it's rare you're going to get a segment with that few addresses that you're never going to add to, or you're just going to add 1. And what you don't want to get into even 6 months from now, or a year from now, or 2 years from now, is a scenario where you have to reconfigure your IP addressing scheme because you don't have enough addresses. So again, in the real world, leave yourself enough room when it comes to subnetting. Here, we're going to go ahead and use just 3 host bits, which gives us a subnet mask of /29. And the result of that, the network itself is 150.51.96. But again, keep in mind with the broadcast address, you're setting all 3 host bits to 1, but the 64 and 32 bit are already set. So that gives us a broadcast address of 150.51.103. So we'll go back to our chart and put that on there. And again, just as a reminder, you want to be really careful with that, because anytime that your broadcast address is lower than your network number, there is a problem in there somewhere. And you can see now we're configuring real variable length subnet masking. And the network address itself will be 96. The valid hosts will be 1.97 through 102, because our broadcast address is 103. And you can already see where this is going with network E, because if the broadcast address for D is 103, then you know it's going to be 104 for network E. And we're going to use a 30-bit mask because we're only asked for that one to have 2 valid host addresses. And according to the formula, we need only 2 host bits to make that happen, so we can use a 30-bit subnet mask. And this ties us down to exactly 2 addresses, so this better be a point-to-point network, obviously. We've got a network number, 150.51.104, and the broadcast address is 150.50.107. And it's a really good idea to keep a chart like this, again, for future reference. Because maybe somebody comes in a year from now and looks at your network and says, I wonder how they got this value, or, what they were doing here, or I wonder what they've already done. Because the one thing you don't want to try to do or have to do on your own is go out in a network map and find all the little subnets somebody else configured. It's not what you want to do. So it's good professional courtesy to keep a chart, and it's smart for you too. So there we are. That is how we develop a variable length subnet masking scheme. I'll put a /30 right there to make it official. And that's how it's done. Now again, I want to reiterate, as with everything to do with binary math and subnetting, and really everything you do in this course, but especially this, the only way you get good at it is by doing it. You can watch me all day long, you can watch this video and it'll show you how to do it, but I would not watch this video and then just go take the exam. I would get some practice in it. You do not need to spend a bundle on practice exams to get practice with this. You can actually make up your own questions. Just practice it. What if you were given the network number 210, just to get you started? Let's say that you had the network number 210, 14, 15, 17, 0. And just make up some questions. Say, okay, if I needed 175 hosts and 100 and 90 and 65 and 37, what VLSM scheme would I develop for that? That's the way to do it. Get some practice on your own. By doing that just a few minutes every day before you take your exam, spending maybe 15 minutes on it at lunch, do 1 or 2 of these a day, you will be amazed at the confidence and the skill and the speed that you develop, because everybody wants to do everything fast on exam day. But you know what the mother of speed is? Skill. If you're good at it, you don't have to rush because you're fast anyway. Let's take a look then at more than you ever wanted to know about how RIP version 1 and IGRP handle routing updates. This is valid material to know. You may never run these two protocols in your life, but it's good stuff to know being a CCNP and building your knowledge base for future certifications, because RIP version 1 and IGRP don't support subnet masking. They have to make some decisions when a routing protocol update comes in that protocols that do support VLM don't have to worry about. The first question or first decision that a router has to make, and again it's running RIP version 1 or IGRP, the question is the subnet contained in this update part of the same major network number that the address on the interface that actually received the update is part of? If the answer is yes, the subnet is placed into the table. If the answer is no, the answer is next question, because there is literally another question that will be asked at that point. Let's take a look at that at a scenario involving that, though. And again, this is something you don't give a whole lot of thought of to with RIP version 1 and IGRP at the CCNP level, but I would give some thought to this. So the question here is, when router 3 sends an update for 150.120 to router 2, is it going to accept it? Is it going to summarize it? Is it going to keep the mask? Let's take a look at that. And here we have router 3 in this scenario. And again, routers 2 and 3 are connected via 150.110, and router 3 has actually a loopback that I configured here in 150.120. And what we want to see is what happens with router RIP. And notice that this time I am not, and that should be a 1, I am not putting no auto summary in. I'm not hard coding for version 2. We're sending and receiving version 1 and accepting versions 1 and 2. Send 1, receive 1 and 2. But obviously, since I didn't change anything, both routers involved are sending version 1. So just with that command, let's go over and see if router 2, which is already running RIP, sees anything yet. Not yet. Show IP route RIP. Let's do a quick show IP protocols. That would do it. 150.100. So now they're both running RIP. We'll clear the routing table because it's going to take a few seconds for our update to show up here. And there it is. So the question here was, is the subnet in this update part of the same network number on the interface that received it? And here the answer is yes. They're both part of the major network number 150.100. So you could see that while we say that router 1 doesn't support RIP version 1 doesn't support VLSM, you can see some subnet information in there. We're kind of seeing that here. So what would happen then if it were not part of the same major network number? Let's look at this diagram where router 3 is going to be sending an update for the network 100.110/24. And it's going to be sent to R2 via RIP. what will the result be? What will router 2 do? Let's take a look. Let's go over to 3, and we'll configure RIP for the network 100.1.0.0. We'll clear the routing table here on router 2. We see it, but it has been summarized. It's been put in with a classful mask. Because the question at that point was not, is this part of the same major network number as Ethernet 0 is already on, because it obviously wasn't. So now the question is this subnet in this update, does my routing table contain any subnets of this major network number that were learned from interfaces other than E0? And I know that's a long-winded question. You didn't know that RIP and IGRP went through this much, did you? Does my routing table contain any subnets of the major network number that were learned from interfaces other than the interface that received it? Well, if the answer were yes, if in this table router 2 already had a route for the major network number, if the answer is yes, if it had any subnets of 100.0.0.0, it would actually get rid of it. It would not accept the update. But instead what happened is that the answer is no, and then the router placed the route into the table with the classful mask. Good stuff to know for RIP version 1 for exam day. It wouldn't hurt a bit. For down the road, doesn't hurt a bit either to understand exactly what RIP v1 and what IGRP are doing there. And you'll notice I wanted to show you one thing too. I see this on the web once in a while, so I just wanted to clear it up. You'll notice that I did use the command network 100.1.0.0 on router 3, but it still took it. Sometimes, since that's a class A, people think, well, I've got to type in network 100.0.0.0, but you don't have to. You can type in the network number, and it's going to summarize it anyway in the command. There's 150.1.1.0. And there's where I typed in network 100.1.0.0, and the router took it, but if you look in the config, it's going to say network 100.0.0.0. So it's not the end of the world if you put the more than the classful number in there, because the router's going to summarize it anyway. And speaking of route summarization, we're going to revisit route summarization a bit. Now, you will see this throughout the course. You've already seen it in some of your routing protocols. When you get to BGP, you're going to see it in there as well. It's an important skill for the real world and for your exam. And why? Well, we've mentioned a couple times through the course that my personal favorite reason for it, the most obvious reason, is that it keeps our routing tables concise yet complete. Routing will still take place effectively, actually more effectively than having a large table. But the table is kept small, and that always helps the speed of the routing process. Now, summarization has another less discussed benefit, that it also helps lessen routing table recalculations when a summarized route flaps. And by flapping, we simply mean a route that becomes unavailable for a few seconds, and then available for a few seconds, and then unavailable, and it goes back and forth. Now, I don't use route summarization to hide a flapping route. I mean, if I've got a flapping route, I want to go fix it. I want to go find out what the problem is. But the key here is that, let's take OSPF for instance. If one area is advertising a summary route, and it's a summary route that includes 8 routes, 8 more specific routes, summarizes them. If one of those 8 routes goes down or flaps, then the LSA recalculation across the network is minimized because the summary route will still be advertised. That router's not going to have to recalculate and send out a bunch of new LSAs and then have that keep going downstream. Now, of course, that network won't be available, and that's going to be a problem. So you want to get a flapping route fixed as soon as possible, and you're not really hiding it with summarization. But it does help to lessen your routing table recalculations. And one question you may have at this point then is say, well, Chris, this summarization is so great, and you like summarization so much, why do we always turn it off when we configure RIP version 2 and EIGRP? Why do we do that? Well, I'm going to show you in just a moment. But before we do that, we need to keep in mind that RIP version 1 and IGRP actually do perform summarization at classful boundaries as well. We just can't turn that off. And we tend to think, well, what are the protocols that do classful, network summarization? It's RIP version 2 and EIGRP. It's also RIP version 1 and IGRP. We just can't do anything about that. So let's look at a scenario then with route summarization. We're going to look at how to summarize routes here in just a moment, just a little review. But here is what happens if we leave auto summarization on. And I have EIGRP here. It would work the same way with RIP version 2. Leaving auto summarization on here, the router to the left has two subnets of the major network number 20000. Since it's advertising them across a classful network boundary, when the router on the right gets them, it'll be a single routing update for the route 20000/8. And in this scenario, that's not bad. And you may wonder, well, Chris, why is that bad? Because then the router on the right will have one route instead of two. Right now, it's not bad. But what's the phrase that I've been repeating quite a bit for this particular video? Future network growth. We don't do this stuff on an island in production networks. We've got to think, what happens if we do such and such in the future? And one reason that we use subnetting is to allow the use of discontiguous networks. And a discontiguous network is simply two subnets or two instances of subnets where of a major network number that are separated by another major network number. This allows us to use subnets of the major network number 20000 in different physical parts of the network. So let's say that 6 months from now or a year from now, someone else comes in and you got a new router and it's going to use subnets of 20000. Makes perfect sense. You're thinking, well, let's go ahead and just keep using these subnets in numerical order. So we'll put 2300 and 2400 down on this other router. Well, now we've got a problem if we didn't turn auto summarization off, because both of these spoke routers here, if you will, are going to be sending a routing update for the major network number 20000/8. And the hub router here is going to say, hey, I'm getting the same exact advertisement from two different points, assuming that the metric is the same. What is EIGRP going to do by default? It's going to perform equal cost load balancing, and you've got a mess. Now, if the metrics here were not the same, what would happen? Something equally as bad. You'd only have one of those two paths, and the other router just wouldn't get any traffic for either one of their subnets. So whether we have load balancing or we have only one path being used, we have a mess. Because if we have unequal metrics here, one of the routers is going to get all the traffic for 20000. If the metrics of these two paths are exactly the same, we're going to have equal cost load balancing. This is why EIGRP and RIP version 2 auto summarization is bad. Because you want to be the one determining where route summarization takes place. You don't leave it up to the routers, and you don't leave it up to the routing protocols. You've got to take action here. And again, you may be in a scenario where we were looking at here, and you say, hey, that's no problem. I'm not going to turn that off. But it could cause trouble down the road if someone isn't really watching what they're doing. So while I don't know what your particular company's policy is on that, but a lot of organizations out there just turn auto summarization off on EIGRP and RIP v2. It's the first thing they actually type before they type the network numbers, because this is what you want. And this is with auto summarization disabled. You've got the subnets being advertised across classful network boundaries. This is what you want, because then you'll have accurate routing to all four of your subnets. Now, looking at route summarization, I'm going to revisit a problem that we looked at in the RIP section, where here we've got 4 routing updates, and we're going to create a summary and advertise it out the interface, since this was RIP, with the IP summary address RIP command. We come up with a summary for this, and there's no problem. Let's review that one more time. It's worth reviewing. How to summarize routes. next to the four network numbers there, I've got them written out in binary, and all we do is look at them from left to right and determine at what point the four routes no longer have a bit in common. And it's right at this line. So now we actually have the value of the summary right in front of us, right? It's 172 for this octet. It's going to be 16 for this octet. And then for this one, it's simply the value of all bits set to the left of that line. And it's 8. Because the 8 bit's the only one set to 1, and then everything else is a 0. So that's actually our summary, but then we have to come up with the summary mask. And you can see that I've already done that here, because to do that with the summary mask, your summary mask is going to have a 1 for all the bits that the routes have in common, and a 0 for everything on the right side of the line. So the full and proper summary here would be 172.16.8.0/22. So summarization is just that quick, and what we went through here and what we walked through is very similar to the kind of question you got on your CCNA exam. And it's important to know how to do the basic summarizations so you can look at more advanced scenarios and spot issues in advance. Because that's another skill that you really want to develop as you earn your CCNP, and especially for those of you with an eye on the IE down the road, you've got to be able to spot problems in advance. We could be asked a question or presented with this in a workplace where we were presented 14 routes. How many routes have we got here? We got 12 routes here, and you can have a supervisor come to you, a network manager, coworker, and say, you know, we're advertising all these routes. Can you come up with a summary for this? And I'm sure that you could come up with a summary for whatever they gave you. The key is, though, you've got to make sure that this summary doesn't include networks that you don't want to summarize. And it's really for the same reason that we turn no auto summary off with the IGRP, even when we just had the 2 routers, because you don't want to include networks in a summary that don't exist yet, because they could be configured 6 months down the road in another part of the network. And you're going to see what I'm talking about as we walk through this example. Here we've got 12 contiguous networks. I mean, the numbers are consecutive from 8 through 19. We didn't skip any here, and I just summarized the number 100 once there in the middle, and then of course that last column is the second octet. We know the last 2 octets for all of these are zeros, so we do not have to write those out. But the question could be, how can we summarize these routes? And from what you've learned so far, and what I used to think as well, is that you just go, well, let's sit down and we'll just go from left to right and see where the columns no longer have a bit in common, I should say. And it's right here, actually. So we'll just summarize the routes with this. Well, that's not right either, right? So we got to go one more to the left if we were going to try to summarize all these at one time. And if you're really eagle-eyed, you can already see where there's going to be a problem here. Well, okay, here's where they no longer have bits in common. It's to the right of that line, because the top 8 addresses have a 0, the bottom 4 have a 1. So we're all set. So we go through what we just did, and we say, okay, you know, first off, what is the summary route itself? What is the summary address? Well, the value of this to the left of that line is 100, 0, 0. So that's our summary. And our mask is /11 because we've got 11 bits to the left of that line. So it's 100, 0, 0/11. And we're done. Well, there's a real problem with this. And the problem is that, yes, this summary does include all of the networks you see on this board. It includes 8 through 19. It also includes 20 through 31. Because if we just in the future came in and said, okay, we're going to put 20, 21, and 22 here at the bottom, Well, if 20 is this octet, the second octet, what does it look like here? 0, 0, 0. And then on the other side of the line, 1, 0, 1, 0, 0. I'll move that a bit to make it a little clearer. So that's a problem right there. And networks 21 through 31 would all fit in this summary. They're all represented by the summary route we came up with of 100.0.0.0/11. Well, we don't want that, because what if we had this scenario? Let's say this is the router advertising the summary. And we'll just put a quick Ethernet segment up here. So we have that. We have those routes being advertised by this particular router. But then later we come along and we add another router to another part of the network. And maybe one of the networks that's lying right off its Ethernet interface is one of these networks that didn't exist when we wrote this summary, but it exists now. Well, now you've got a problem. If you've got the summary being advertised out here, and you've got a more specific route coming in from here that fits that summary, you got a real problem. So you see what I'm driving at here is that when we are coming up with this summary route, we've got to be really careful not to include routes that either don't exist yet or that may actually be found in other parts of the network. So what we're going to do instead of all this, let's clean this up. What do you think we should do here? What's the best solution for this? Because that's a lot of routes and you can't actually summarize it. But what you're going to do instead is come up with two summary addresses. There's nothing wrong with that. You're going to look at one set of addresses and summarize them and make sure that no other networks are represented by the summary, and then see if you can do that for the second one as well. So let's move network 20 down here, because we're going to come back and refer to that in a few minutes. First off, let's summarize those top 8 routes. And what you could do is, you draw this out in binary and you just go off by yourself somewhere and take a look at it, or in the exam room, just take a few minutes extra here, because you'll have plenty of time, you'll be well prepared. We can summarize these 8 routes without any possibility of another network fitting into it. And you know how we can tell? Because the last network being summarized here is all ones to the right side of that line. There's no other route that will fit this summary. If it were 7, if we went down 1 to 7, this wouldn't work for network 7, because this bit would be a 0 to the right side of the line. It wouldn't fit the summary. If we went 16, obviously since 16 is right there below 15, we can see that this would not fit the summary. It wouldn't match up with the other 8 routes on the left side of the line. So we can come up with a summary for these 8 networks. And what does that end up being then? Did you catch it? Yeah, watch that. Good stuff. There's where our line is. And we have, to the right of that line, we have everything from 0, 0, 0 to 1, 1, 1 and in between. Nice catch. So, what's that going to be? 100.800 is the value of everything to the left of that line, and it's a /13. That's your first summary address. And again, the key here is no other network can fit in that summary. 7 would not fit in there, and 16 would not fit in there. So now let's take a look at those bottom 4 routes and see what we can do there. And it looks like if we go from right to left, this is where they no longer have bits in common. And again, we are successful in the fact that no other route can be represented by this summary, because we've got 0, 0, 0, 1, 1, 0, and 1, 1. We have every possible combination of digits after that right line already represented in this octet. So if we try to summarize with network 20 the way we did before, it wouldn't work. Because when you bring this up, what's the problem? It's going to have a 1 to the left side of the line, where all the other routes have a 0. So we are going to be able to come up with another summary then. And what's the value of that summary? 100.800 108.0.0/14. So we came up with two separate summary routes, 108.0.0/13, 116.0.0/14. Now, this is still great, because now if you advertise that summary out the router on the left down here in the little diagram I drew during this lecture, that router, instead of advertising 12 separate routes, is going to send out two summaries, and there's no real limit to the number of summary addresses you can put on an interface. I wouldn't put 30 of them, but hopefully you're not trying to do that anyway. You could easily put both of these summaries on with the IP summary address RIP command. There is no problem with configuring two summaries on a single interface. And the downstream routers now, instead of getting 12 separate entries, they're only getting two summaries. But keep in mind, for both your exam and for the real world, especially for the real world, summarization is not always going to be nice and neat, and you're going to come up with one summary route that's going to be perfect. You may have to go with two. You might have to go with three, but you can probably get the job done with two. But the key is, two routes in a router's routing table is a lot more efficient than having 12. Finally, we're going to talk about CIDR. And CIDR is classless interdomain routing, and classless interdomain routing is prefix routing. Okay, it's two names for the exact same thing. And there are some really long-winded explanations of what CIDR is out there. So I have summarized for you right here. Speaking of summarization, this is what CIDR is. All it is subnetting and summarization performed at the Internet Service Provider level. That's it. That's what it is. When you're performing CIDR, what you're doing is working with route summarization, you're working with subnet masking, but that's all you're doing. It's developing a VLSM scheme and then coming up with ways to summarize it. Now, CIDR is obviously going to be a larger scale of subnetting and summarization, because you're doing it at the Internet Service Provider level. But essentially, they're the same thing performed at different points. We perform route summarization and VLSM at the network level, and the ISPs do it at their level, and they call it CIDR. If an exam question asks you to work with CIDR, or someone says, oh, we're going to do some CIDR, don't panic about it, because it's all subnetting and summarization, and you're a CCNA and a CCNP, you know how to do that.